Okay, on tonight's laboratory exercise, we're going to be playing with oscilloscope, show you the basics of the oscilloscope. Right now, I'm just playing with what are called Lissajous patterns. And uh, as I was telling the class back in the 50s and 60s, when I was a kid, these Lissajous patterns were very, very common um, for just in common displays in um, science fiction movies. Let's see if we can get this one to move a little bit. All I've done on the, uh, let's see, I think the x-axis, uh, the the channel one is the x-axis. That's the one that's at 300, and it's steady. And channel two is at the 302. Oh, what I do? I'm changing the voltage. I don't want to do that. I want to change the frequency. And you can see as I change it, it basically what it's doing, it's showing you a phase relationship with the two inputs. So we've got right now, I'll set it back to 300. Now they're both in sync. The bottom one's at 300 and the top one's at 300. Now let's change the top one to something like 450, which is 1.5 times. Oops, wrong way. 450. There's a nice little pattern. And if we just adjust it a little bit, we'll get some movement, and it makes it look like it's rotating. When I was a kid, there was in fact, I think you can probably even look it up. If you look up Project Terror on YouTube, they have the intro to Project Terror, and it was kind of a Lissajous pattern. Friday nights, it was a scary movie night, and they had a show called Project Terror, and it would show you. This may not be the Lissajous pattern that they were showing, but it was just look up Project Terror on YouTube, and I think you'll find the video. So let's take it out of. We're just playing with Lissajous patterns here. Basically, what we've got is we've got 300 cycles going here, and we've got 450 here. If I put it exactly at 450, it'll lock and stop. So do I have that right? Let's see. This is, because it looks like there's twice as many on the Y as there are in the X. I'm a little confused, but that's okay. It's just we're just playing with it now. Now let's take it out of this this mode off, and now we're just looking at regular waveforms. Let's just look at yeah. So we've got the oops, let's change this to, we'll put them both at 300. 300, and you can see they're not quite in sync, but with this you can measure, a DC, a multimeter like we've been using in our previous labs. They're great for measuring, just DC circuits when we're using just batteries or a power supply set at 5 volts or 10 volts. You can use a multimeter. But once you start getting into waveforms, into signals, 300 hertz, 500 hertz, or even 100,000 hertz, they're not going to do you much good. the multimeters will, like I think I demonstrated, you can plug it safely, plug it into a wall, and you'll measure the 120 volts out of the wall that's going at 60 hertz. That's a low enough frequency that it doesn't, it's able to measure that. But if you, and I forget what the limit is on a multimeter, it might be 1,000 hertz or so. Once you get to 1,000, it's not really reading correctly. Hello there. So when you start getting signals, we're going to be using an oscilloscope. So this is basically an oscilloscope lab. And let's put one of these. Oops, I think I turned the wrong. Well, let's see. I turned the wrong one off. Let's set this back to something like 300. And let's turn this on standby. Output standby. And I don't have any voltage. That's why it's okay. Let's put it in auto set, and it should. Let's do that again. Auto set. And let's go to the horizontal and close that up a bit. Let's position it. Right there, and let's raise the voltage. There's 2 volts, but you can see as we adjust the frequency, the oscilloscope displays what's going on. This function generator, I want to discuss a little bit about the function generator, and I've got this on the handout. How many of you have, if you haven't looked at it, it's fine because I just sent it out recently. How many have had a chance to look at the write-up on the oscilloscope lab? Anybody? No? Okay, good. It does have different waveforms, and we'll go through those. Right now, we're looking at sine. You can do square wave, and we're going to be working with a square wave today. You can do triangular wave. You can see right there, and you can do a positive ramp. See, it's ramping up. It's a positive going ramp, and you can do a negative ramp. Now it's going down. I mean, once it finishes its downward ramp, it goes up to the top and it ramps downward. And I think there is, well, we don't want DC. And you can also modulate it. There. Let me take this off. Okay, the purpose of this exercise is just to familiarize you with a general purpose oscilloscope. It's going to introduce you to the multifunction generators, and that's what I've done. So this is a Pasco PI 8127. Then we have the Tektronix TBS 1072 oscilloscope. And then we're going to have a proto board, the one that we've been using in the lab. And I pretty much already have said this, a multimeter was useful for doing direct current. For when you start getting to signals, then you need an oscilloscope. And here's the function generator. The function generator, I've already showed you, these can do sine, square, triangle, positive ramp, and negative ramp. And we're going to use these 2 devices to measure frequency, period, an RL time constant, and an RC time constant. And we're going to try a little experiment with resonant frequency. Now, this is stuff that I just tried 2 weeks ago when y'all were here doing the inductive electromagnetic induction. So I'm still working on it. So the first thing we're going to do is we're just going to measure. We're just going to use the function generator, plug the function generator into the oscilloscope and measure the peak to peak amplitude, the frequency. We'll have it set on the function generator, and we're going to read it off the oscilloscope and see if they agree. They should, or be very close. Then we're going to increase the frequency. It defaults to 1,000 hertz. We're going to go maybe 2,000, 2,500, something like that, maybe even 10,000, a different set of frequencies, and then go through the same sine, square, and triangle, and see if there's what we measure. Then we're going to do an RL time constant, and I tried this last week, and if you can see that little pink solenoid that's on the proto board, that's what I use. That's going to be our inductor. So you place a function generator, the 1,000 ohm resistor, and the proto board solenoid in a series loop. You set the function generator square wave, and you can adjust the function generator frequency until a full cycle is shown as shown here. I only did it with RL. I didn't do it with the RC, so I don't have a figure for the next section. You use the cursors to determine the 37% point on the downgoing waveform. Why 37%? Who can tell me why 37%? Nobody? That's 1 tau. 1 tau, one time constant for an RL circuit is when it reaches 37%. Or the other way of looking at it, it's down 63%. Using the time it takes to reach the 37% point, determine the time constant R. Now, using that measured time constant, we can determine the inductance of the solenoid, right? So now that we know that solenoid, we can, we'll use that for the step following. And then we're going to do an RC time constant. We're going to use the same resistor and then just some capacitor. Now, if you recall, when we did our RC time constant, we used large values just because it takes, we were doing the measurements by hand and a stopwatch actually we were just using the timer on the phone and coming up with the time constants. And I don't know about y'all, but I think when I went through it, the errors were pretty large on that particular lab. And we're going to try it with with this function generator using the square wave. So you place the function generator, 1,000 ohm resistor, and a capacitor in a series loop. Set the function generator to square wave, just like we did in the previous one, and adjust the function generator frequency until a full cycle appears. I didn't set that up, but we're going to try it today. Using the cursors, determine the 63% point on the upgoing waveform. Why? Because it's charging. We're going to look at it charging. So we want the 63% on the upgoing waveform. Using that time that it takes to reach the 63%, determine the time constant tau. Compare the measured time constant with the calculated time constant. If we have 1,000 ohm resistor and something else, a 47 microfarad, we should be able to calculate the time constant. And I've got spaces there for you to put those values. The resistor, it doesn't need to be R1. There's only R1R. The tau measured and the tau calculated. I should have a percent difference in there, but I don't. Now, we've tried to determine in that second, the the second one, we tried to determine the inductance of the solenoid. Using that value of inductance and the capacitor that we use, let's try to figure out what the resonant frequency is. We had, remember this this formula, the F sub 0, the resonant frequency is equal to the 1 over 2 pi the square root of LC. And let's see if we can calculate what the resonant frequency should be, and see if we can see it by setting up a circuit. And after that, we're done. So any questions? No questions. Okay. I did print out some of the just these last 2 pages. I printed out those. You don't need the introductory page, but I did send them to you. Okay, if there's no questions, we're going to go ahead and stop the video, and I'm going to try to, for the fellow that wasn't able to be here tonight, I'm going to try to record what happens when we do the experiment. Okay, let's stop share and